Okay, so let's go ahead and start. So this is an overview of patterns. So if you take a look, what we're going to do here is we're going to talk about the importance of experience in trying to master complex things. That's basically the context here. We, of course, are going to be talking about the importance of experience with respect to building software, but it's worth taking a step back and looking at other kinds of experience that is useful for other things. So many people here probably have other hobbies and other interests besides writing software programs, right? So if you like to play music, if you are into various kinds of athletics, if you're into martial arts or dance or almost anything that requires a tremendous amount of practice and skill to become good at, then chances are you discover that you, as a beginner at something, maybe behave differently than someone who was an expert, or maybe yourself as you became an expert. So, for example, when I was in graduate school, I took Latin dancing. I was in California, and it was a fun thing to do. And I took a Latin dance class, and I got reasonably good at Latin dancing in the dance class. I could do simple things. And then one night I went out to a salsa club in Costa Mesa, California, where people really knew how to Latin dance. And it was pretty intimidating because they were not doing the kinds of things that we had learned in the dance class. They were doing much more sophisticated stuff. And that's because I was still sitting there counting in my head, and they had been doing this for 15, 20 years, and so they were really, really good at it. And they didn't have to stop and think, right? They weren't sitting there going, 1, 2, 1, 2, 3, or stuff like that. They were just basically living out something that they practiced as an art form for decades. When you think about this stuff, when you start to watch, you forget how much effort it took to get to that point. There's a great book by, Malcolm Gladwell about outliers, and he tries to make the point in the book that to be really good at something, you have to spend a lot of time at it. I think he says 10,000 hours, just to pick a number. Who knows whether it's 7,000 hours or 12,000 hours, but it's a lot of time, right? And he uses examples of things like the Beatles and other people who became great at their art, and you would go and see the Beatles in 1965 and think, wow, these guys are really great, which they were, but you didn't realize that they've been doing that since the late 50s. They've been practicing for a long time. So sometimes it's easy to forget how long you had to work to get to a point where it looked easy, right? Crucial to all this is continual repetition and practice. So another thing I did when I was an undergrad is I took karate. And so one of the things we did when we did karate was we started out with very basic moves like punches and blocks and kicks, and we would do those over and over and over again, kind of like the Karate Kid, right? Wax on, wax off, and all this kind of stuff, until it becomes second nature. And after a while, you start to string together these movements into patterns, right? So they're called katas, and they're groups of punches and kicks in certain orders, and so on and so forth. And the point there was that the experts could do these things fluently and fluidly, and us white belts had to struggle and think about every step along the way. And the only way to go from being a white belt to a black belt was through practice and repetition. It also, of course, helps to have mentoring from other experts. So if you learn to play music, you're often learning from a person who has more skill than you. If you have a coach, conceivably, in learning to play soccer or tennis or basketball or football, you're learning from a person who has better expertise. And so it should be no surprise at all that when you're trying to learn to be doing software, it helps to learn from people who actually know how to write software. So let's talk about writing software. What does it take to become a master of writing software? Well, if you didn't know any better and you went to a different school than Vanderbilt, you might come away from that experience thinking that you need two things to become an expert software developer. One is knowledge of programming languages and other such stuff. And you would discover that a lot of places spend a lot of time focusing on that. There's nothing wrong, by the way, with learning about programming languages. They're very important. Just like there's nothing wrong with learning about algorithms and data structures and all the basic core theory and underlying concepts. But if you're not careful, knowledge of programming languages can get you into trouble. And let me give you a couple of examples. When I was first learning programming in a major way, it was sort of the late 80s. And I had an unusual background. I'd gone to the College of William & Mary and was a sociology undergrad major, and then I got a master's degree in sociology. And along the way, as I think Lawrence and I talked about the other day, I was saying I realized what was I going to do with a master's degree in sociology? Not a whole lot, right? So I decided I would switch to computer science. And so I spent a lot of time learning how to program and other things, which was really fun. But along the way, I started to write these cool programs. And one of the programs I wrote, one of the first things I wrote that really had an impact was something called gperf, which is a perfect hash function generator program. So it generates perfect hash functions. Given a set of keys, it'll give you a hash function that will look up the keys in constant time to figure out whether another key is in that set or not. And this has actually been used in a lot of different things. It was used for a while in the GCC compiler for doing compiler reserved word lookups and other stuff. And I was pretty proud. I wrote this thing. I wrote a paper. It was kind of cool. And I designed it. I was really learning C++ and object-oriented design at the time, so I had an interesting organization of stuff. But there was a problem. The problem was when I wrote the code, even though it sort of worked, I made a lot of mistakes. I hard-coded the algorithm, so there was just one way to do the perfect hash function algorithm, which was inadequate for certain use cases, for certain kinds of keywords sets. I also hard-coded the data structures. I hard-coded the generators that spit out code in different languages. So when I went back later to make changes, it was a lot of work because I had painted myself, or I programmed myself into a corner, right? It was something where it met its original requirements, but it was very hard to evolve, very hard to maintain. Now, I managed to solve this problem in two ways. First of all, I was doing research, so I wrote a paper on it that got accepted. And secondly, I turned it over to the GNU Software Foundation, and they maintain it now. So the Free Software Foundation maintains gperf. If you go look here, you'll find it. It's part of their release going a long, long way back. And hopefully somebody along the way has come along and fixed it and made it better. But the point was that because I was so enamored with C++ language issues, because that's what I was learning at the time, I didn't really stop to think very much about design, and that kind of bit me. Another problem you run into when you start getting into love of programming languages is you start getting really wrapped up in their obscure features. So here is actually a winner of the best one-liner from the 2006 Obfuscated C Code contest. Now, we don't have enough time. We would probably take an eternity to do this, but we don't have enough time to figure out what this program does. It looks kind of like line noise, right? It looks kind of like the output you get from a dial-up modem when something's gone wrong. Anybody want to guess what this does? Close. It frustrates people. It definitely frustrates people. This is what it does. When you compile it, it prints out the time in military time of when you compiled it. So that's actually the output of running that program through the compiler and running it, right? Never would have guessed that, would you?
Isn't there a programming language, Malboj, that is designed to look like complete nonsense?
A lot of people probably, write in that language whether they know it or not, right? You can take a look here. There's actually a website that has examples of all the winners from the Obfuscated C Code contest, which is pretty funny. Anyway, that's the other problem. People get carried away with the language features. So that's one set of things that people get led astray on. They think, oh, if I know the language really well, I must be a good developer. Or if I know algorithms really well, or if I know data structures really well, I must be a good programmer. By the way, I'm not saying don't learn your languages. I'm not saying don't learn algorithms, data structures. Those are really important. You've got to know them. Some languages make things easier than others. But that's necessary, not sufficient. At the other end of the spectrum, which you might also get a feeling of if you went to certain schools, is you might think that what's really most important in being a great software developer is knowing how to draw pictures of your design. So there's a whole school of thought that talks about the Unified Modeling Language, UML. And UML is a way of trying to describe in a visual form the software designs that you would otherwise write in a programming form. And again, there's a time and a place for this, right? So you can draw what are called sequence diagrams that illustrate the ways in which various roles interact with each other, classes, objects, functions, etc., talk to each other, interact with each other. You can show various structural relationships between things. Here we show relationships between various entities, showing inheritance or association or containment or other kinds of relationships between various entities in a program. Useful things to know. But just because you can draw lots of pretty pictures with some kind of modeling tool doesn't necessarily make you a good programmer. Just because you could draw pretty pictures of rooms and houses doesn't make you a good architect. We built a house starting last year. And one of the things that was most interesting about that experience was that we designed the house using a CAD package called Floor Planner. It's basically a cloud-based CAD package for designing houses. And that's pretty cool. You can do stuff. But what you discover, first of all, you can really only do the floor plan, right? So you can kind of draw the layout of the rooms. But when it comes to the structural elements of the house, right, where do you want to put the support so it doesn't collapse on itself? When it comes to putting, where the plumbing goes, where it comes for putting load-bearing walls and R values and insulation and the N zillion other myriad things you have to do to make a house really work, drawing pretty pictures in a CAD tool is insufficient, right? It's nice, it gets you part of the way there, but it doesn't get the house built. You need an architect that really understands how to do that, and you need a lot of other things too. By the way, I just have to point out, a lot of times when you talk to people in other disciplines, they always complain about software, and they say, software, it's always late, it's always buggy, people never seem to quite know what they're doing, we don't really have any good insight as to whether we're making any progress or not, unlike real disciplines like building houses. We know how to build houses, and we can draw the plans, and it just works. Well, I'm here to tell you that's complete hooey. You discover that there are mistakes in architectural diagrams that come back to bite you. We discovered that a number of times. We discovered that the people who do the building, despite the fact that we've been building houses for hundreds or thousands of years, not every single person who's building a house has built a house for hundreds of thousands of years, right? Not every person who builds a house is paying attention when they're doing something. People spend time cutting corners. Things don't fit. You have to spend a lot of time redoing stuff. It's very expensive. So all the things that we complain about software are actually also true in the physical world. It's just for some reason you can measure progress by how high the foundation is, and so you feel somehow more assured that you have control over the situation. But it's still just as fraught with mistakes and human error and all the imprecisions that we've come to expect in our world as well. So the point here is that making good software, designing good software, is more than just knowing how to draw pictures. And people who are good artists aren't necessarily good architects. So the bottom line is, what is useful, right? What is worthwhile? What can you depend on? So what you really end up being able to depend on is experience. And that's really at the core of what makes someone better than someone else. And experience in many ways. Experience as a designer, experience as an architect, experience as a programmer, experience as a manager, and so on and so forth. And that experience is at least as important as knowledge of languages, algorithms, data structures, environments, modeling tools, etc. And I've learned this many times throughout my career. When I was a graduate student at the University of California, I did some consulting work at the time, and I was working on a project for a company that was doing call center management software. These are things you'd use to keep track of call centers. How long are the calls in queue? Are your operators busy? Have you got sufficient capacity for the load that you're experiencing when people call up, et cetera? And so I had helped develop some software, and at the time, this was 1993, we were using Unix, we were using Solaris. And so we had built this interesting system that allowed us to manage a certain kind of private branch exchange switch, a PBX switch, using Unix-based software, which was pretty cool. And then one day I came to work, and the boss said, hey, we got a meeting today, and I was new, and said, oh, great, a meeting, this is fun. So I went to the meeting, and they said, we've decided that we're no longer going to be using Unix, we're going to switch over to Windows NT. So we went from this to this. Well, none of us on the team who'd done all this development had any idea what Windows NT was at the time, which was not surprising because it really had just been released. So we were a little nervous. We're like, oh gosh, I don't know if we'll be able to be useful. Maybe we'll lose our jobs, etc. But it turned out that because we had developed the software using patterns and frameworks and other good abstractions, extra levels of indirection, as it were, we were able to take our software and port it to Windows NT very quickly. And so we were able to stay employed, which was great. I'll tell you a story later on. There's some more to the story that comes along at a later point. But the point there is that design expertise, decoupled from the platform and other more mundane aspects, is often very useful to keep you relevant as the world changes around you. And there's a little paper that talked about some of our experiences there. So where should this experience reside? Well, first of all, what kind of experience are we talking about? What are the things that you can leverage? So some of the things that you can leverage as an experienced software programmer, architect, developer, designer, and so on include things like abstraction, which really deals with emphasizing what's important at a particular layer or level, and then de-emphasizing stuff that doesn't matter at that level or layer. That's what abstraction is about. Remember, we talked about indirection. That's an example of abstraction, not getting wrapped up in implementation details that might change. Flexibility, which is really the ability to take something and apply it in a new context. Reuse, which is kind of the same idea, being able to take something that wasn't designed for one environment and then being able to use it in some other place using things like adapters, as we've talked about. Quality, which of course is trying to reduce defects and make sure the software meets its requirements. And modularity, which is all about trying to break the system up into smaller pieces so they're easier to understand, so they're easier to evolve, easier to debug, maintain, and so on and so forth. Those are some of the things that you learn as an expert that you probably didn't know when you're just starting out. I know I certainly didn't when I started out. So there's a lot of valuable knowledge in all those kinds of things. And where does that knowledge typically reside? That's the big question. Well, historically, this kind of knowledge has resided in one or two places. It's either resided in the heads of the experts, the people who are the experienced developers and architects and team leads, or it's resided deep in the bowels of the source code. So in the Subversion repository, in the GitHub, whatever, that's where the knowledge is. It's all encoded in there. But both those places are very problematic, right? So if it's in the heads of the experts and the expert decides to quit or decides to retire or gets hit by a truck or whatever, then chances are you've lost that knowledge. And I'm sure you probably have worked enough at this point, either through internships or on team projects, where depending on somebody else who flakes out or isn't able to deliver, causes you a lot of headache to try to play catch up, which is very, very troublesome. Likewise, if the knowledge is in the code, wow, that's a lot of work to reverse engineer all that knowledge. If somebody dropped you into the middle of the Linux kernel or Android middleware and said, figure this out, you'd have a lot of learning curve to overcome to get to the point where you could be productive in any way, shape, or form. So to wrap up this little overview, becoming a master of software requires the same sorts of things that you get when you become a master of anything else. You've got to do practice and repetition, and often most places you go to learn about software, most universities do not give you that kind of experience. And that's why it's frustrating when people don't follow the directions, because they can't really benefit from the reviews. You'll probably never again have a class where you get so much feedback if you take the time to do a good job, right? You'll never ever have that experience again, so it's kind of unique. But that's what you would hopefully get if you go work at a good place in industry. If you go work in a good place in industry, hopefully the people there are going to have code reviews and design reviews and mentoring and pair programming and brown bag lunches where you look at the works of other people and marvel and are amazed at what they've done and so on and so forth. It's kind of cool. Nowadays, it's a lot easier. Back when I started, there wasn't a lot of source code to use. Nowadays, it's source code galore. If I want to learn something in Android, when I do my Android course, for example, we look at Android source code. Sometimes we look at the kernel code in Linux. Sometimes we look at the Android middleware. Sometimes we look at the Java virtual machine, Dalvik as it's called in Android. We look at a lot of things, and because the source code's all there, we can figure out what they're doing, and then we can decide whether or not to apply those techniques and patterns to our code that we write as well. So it's very useful to help be more effective. There's also, of course, a lot more resources at your disposal. Nowadays, you get free courses on almost everything that's useful. So obviously, you can take courses here at Vanderbilt, and there are lots of great courses here, but there's also good courses taught by experts all around the world, and you can leverage those things. They just weren't available before. Good software developers leverage designs that have been applied successfully before. So just to finish off my little story, after we developed this private branch exchange software in NT versus Unix, a year later I went to work and they said, we have a meeting. By that point I'd figured out that that wasn't always the best thing in the world. And we went to our meeting and the boss said, the company headquarters has just decided that our implementation is redundant with some other stuff, so we're shutting down this line of work. And we're like, oh no, we're laid off again, right? Mm-hmm. Well, it turned out that they didn't need that particular private branch exchange capability, but they could do some work with a central office switch. So we just took all of the stuff that we've been doing for private branch exchanges, moved it over to a central office environment, wrote a few adapters, started working again, had capability very quickly. So we kept our jobs for a time longer. One of the things, by the way, that you should come away with from this discussion is that there's a lot of great stuff going on in industry, but it's often very fluid. And so you're well advised to future-proof yourself. Things will change. The programming languages you use will change. When I first started learning programming 30 years ago, I learned Pascal. Nobody uses Pascal anymore. When I started using when I started programming 30 years ago, I used an operating system called Prime OS. Nobody's even heard of Prime OS anymore. The notations that we used, the design methods that we used, the middleware or the lack of it we used, all those things have changed many times. Ironically, though, some of the fundamental design patterns and architectural styles that we'll be discussing here, those things are eternal. They were used back then. They're used now. Come back in 100 years, they'll probably still be used then as well. So figure out how to focus on the things that are more stable and then be able to find ways to adapt your knowledge as you switch between different languages and platforms and methodologies and jobs and domains and so on. Very, very, very valuable. Having said that, of course, there are certainly things that differ, right? Mobile device programming is not identical to programming a mainframe. And so there are new things you have to learn. There's location issues, there's security issues, there's wireless networking issues, there's sensor issues, and so on. But many, many things are the same. So by knowing the stuff that's stable, it can give you more time to focus on the things that differentiate yourself and make you have a competitive advantage relative to somebody else who doesn't understand things at that level. So what we need is some method of being able to extract and document and codify and disseminate all of this knowledge that is either locked in people's heads or buried in the source code. So it's a lot easier to get to it without a lot of risk and effort and time expended on this process. Okay, so that's just sort of like the intro to this thing. That just sort of motivates what we're about to talk about. Any questions at this point? Patrick?
What style of karate?
Oh gosh, I don't even remember. It was so long ago. But my sensei was from Japan, and he was like, I don't know, some high-level degree black belt, and he'd reached the point where he no longer was really focusing on the physical aspect. It was all sort of spiritual, and he wrote, sort of haiku, and he would stand in, buckets of ice for hours at a time to test his will and things like that, So it's kind of interesting how those things evolve. Okay, so next topic about patterns. What we're going to do now is we're going to introduce patterns as a way to improve software quality and developer productivity by a number of means. Being able to map design problems to proven solutions, crucially important in patterns. When you come upon a new problem in either the same domain or a different domain, and you think to yourself, gosh, I think I've solved this somewhere before. I've seen this somewhere before. That's about mapping problems to solutions. That's a big thing that patterns do. Patterns also help to identify and name recurring structures. Just like in chess, if you're a master chess player, there's certain openings that are given names. If you're into basketball or football, there's certain formations that people have, right? So there's cover 3, or there's the 3-4 defense or whatever, or the wildcat, right? The wildcat formation. Those are things that an expert in football would go, oh yeah, I know what that is. They're a pattern of arranging people on a playing field to do certain kinds of things. Conveying architectural knowledge. This is one of the most important and valuable things you can do as a software developer, is be able to understand the architecture of your solution and convey it in a relatively unambiguous way to other people who you may work with who need to understand things. Most software fails not because of some lack of an algorithmic insight or some data structure with asymptotic time complexity properties that are incorrect. Those things matter, but they're typically rather tactical in nature. Most software projects fail because people don't understand how all the pieces fit together, which is fundamentally an architecture problem. Just like a house that's put together incorrectly typically doesn't fail because someone didn't use a nail gun or a certain kind of nail. It fails because they didn't get the load-bearing properties of the walls correct relative to the type of the soil or the presence of seismic activity or whatever. Another important thing is codify design expertise. You'll find out that there's only so many ways to slice the loaf of bread, and once you understand those ways, you can be effective at repeating and applying things that are well known, and they're codified, they're systematically understood and formalized. And then finally, the big concept here, enabling systematic reuse. If you take a look at things that we're accustomed to using every day, things like, say, Android's frameworks, or C++ standard template library, or the Linux libc, those are all examples of things that we didn't write. We leverage somebody else's effort, and so they make us more productive. Nobody in their right mind today would start writing a program by building an operating system from scratch. You'd have to be doing something really, really esoteric to want to be able to do that, or you're funded on a research grant or something like that. So the key point there is that people reuse what's already there, but they don't want to just reuse it in an opportunistic or happenstance or random way. You don't just cut and paste stuff. Instead, you want to think about how to systematically reuse software, which means being able to take the pieces and rearrange them in various ways. We're also going to talk about some of the common characteristics of patterns. So first of all, what's a pattern? What's a good definition of pattern? Always good to know for quizzes and stuff like that. So pattern is basically a solution to a common problem that arises in a particular context. Now, not surprisingly, we're going to be focusing primarily on software as the context. But of course, you could get more specific. You could talk about software for mobile devices. And there's ways of programming mobile device software that may be a little different from programming electronic stock trading applications. For example, in electronic stock trading, high frequency and low latency is crucially important. And people are often willing to dedicate enormous amounts of hardware resources to making their programs run really fast. They plug them in, they crank them up, they throw lots of cores at the problem, they solve problems through scale, through parallelism, through hardware assist, and so on. Mobile devices, typically battery-driven, they're getting bigger and bigger in terms of processors and memory, but the power consumption is still a big issue. So people program differently in a mobile environment. You have to deal with disconnectivity a lot. You have to deal with the fact you don't have all the resources in the world at your disposal. So you think about your programming in a different way. Obviously, the other domains, aerospace, avionics, automotive, all these things have different characteristics, and that influences the kinds of problems we run into and the kinds of solutions that can be applied to solve those problems. Just to illustrate the point that not all patterns relate to software, anybody here ever driven in New Jersey? Okay. So what is that funny-looking thing up there? That's called a jug handle. If you go to New Jersey and you drive for any length of time, especially when you get off the Golden State Parkway or the New Jersey Turnpike, you find a lot of these things. You find these in things called jug handles. And it's interesting because they're a pattern of civil engineering in New Jersey. And it's interesting to ask, why do you see them there? If you go to California, you will never see anything like that. And it's interesting to ask, why are they like that? Well, if you think about it, New Jersey is a very old state. At one point, it was the most densely populated state in the country. Certainly, the George Washington Bridge is densely populated at times. But as a result, and because it's old and it's been around for a long time and it's densely populated, the road system evolved organically from footpaths to horse paths to two-lane roads, and then they paved them, right? And that's about what they have. Most places you drive in New Jersey, you have sort of roads where you have a lane in one direction, a lane in the other direction, and lots of buildings and offices and homes and stuff right along the roads. So that causes you certain problems as an engineer. So if you want to be able to allow people to make left-hand turns, which of course you need to be able to do, how are you going to do it? Well, if you were in California, how would you allow people to make left-hand turns in California?
Wide road.
You'd have a wide road with 2 or 3 left-hand turn lanes. And those lanes would be used to queue people up so they could turn left, right? So they wouldn't block the traffic that's trying to go straight. If you only have single-lane roads in each direction, if somebody wants to turn left and most people don't want to turn left, you have a traffic jam, right? Because they have to wait for oncoming traffic. So what they do in New Jersey is, since they can't widen the roads because it would require buying up lots of expensive property, instead they buy some land at the intersections and they build a 7-Eleven or a Mapco or something like that there. And then they make basically what's called a jug handle. So if you want to go left, you simply make a right-hand turn. Ronald Reagan would have loved the New Jersey road system. He never would have to take a left. You never have to be doing anything on the left. Only take a right. There's some joke that he never turned left, but I don't believe that, unless he only drove in New Jersey. So you can basically do the queuing here in the jug handle. That's an example of a civil engineering pattern you find in New Jersey because of certain characteristics of certain forces that influence the way in which they could evolve in that context. So the jug handle pattern is a solution to a problem that arises in the context of densely populated areas where roads are expensive to widen. We, of course, are focusing on software. So let's talk about software patterns and discuss what they do. So one thing you need to be able to do, or one thing that patterns allow you to do, is the ability to name a recurring design structure. So if you take a look here, you can see we have a certain arrangement of entities. I haven't told you much about what those entities are yet, and it doesn't even matter really, but they're entities of some kind. Classes, components, who knows. And we give this thing a name, and this particular name of these entities, when associated like this, is called the observer pattern. So that's the name of this thing, right? It's the name, the observer pattern. And when you hear the observer pattern, this canonical picture should have popped into your brain. Keep in mind, it's not the only picture, but it's a canonical picture. The intent of the observer pattern is to define a one-to-many dependency between objects so that when one object changes state, all dependent objects are notified and updated, or given the chance to update themselves. Okay, so that's the intent. Here's some other things that a pattern gives us. It allows us to be able to specify this design structure explicitly by talking about various relationships between objects and classes. Keep in mind that class and object is used somewhat loosely here. We're talking about object-oriented systems in this class because it's an object-oriented programming class, but you could be programming in C or non-object-oriented languages, and these same things would still be useful. For that reason, people sometimes replace class and object with role and responsibility. So as you can see here, the observer pattern has certain roles and responsibilities. So you can see that the observer, which is the guy that's over here, see if I can use my funky little pointer. There we go. The observer has a method called update, and we can tell by the fact it's italicized that this is a virtual method. So what that says is that the observer role can be updated, and the subject has a bunch of observers. That's what this little syntax means here. Subject has a one to potentially many relationship between subject and observer. And then a concrete observer can inherit from observer and override its update method to do something. So here's something it might do. When update gets called, it might get some data that it gets from the subject. And you could also see some other roles here that the subject has ways of being able to attach and detach observers. And when somebody wants to let folks know something's happened, they call the notify method, and that iterates, using our good friend the iterator pattern that we've talked about with STL a number of times. It allows us to be able to iterate through all the observers that are contained in the subject, and we tell them to update themselves. That's kind of the roles and responsibilities involved in the relationships. It also tells you some dependencies. This tells you that in this particular case, the concrete observer depends on the subject to get data, and the subject depends on the observer to be able to be updated. Their interactions, you can see that the observer can call back to the subject can notify the observers, and there are certain conventions. For example, one of the conventions here is that when you're being updated, you shouldn't block for a long period of time because you'll end up starving other observers from running, at least in this particular implementation, assuming we were using one thread of control. So that's basically what the structure and the interactions of the pattern are telling us. They're specifying the design structure. Patterns also do some other neat things too. They abstract away from concrete elements of the design. Right? We can look at this observer pattern discussion and not know or care whether this is in the domain of financial services, whether this is in the domain of email dissemination, whether this is in the domain of battery management on a smartphone, whether this is in the domain of a number of different things. So we don't have to care about the problem domain. We don't have to care about the form factor. Are we talking about a desktop? Are we talking about a tablet? Are we talking about a phone? The form factor doesn't matter. We can still talk about the design as a design. We don't care whether this is from Apple or Google or Microsoft or anybody, right? We can talk about design somewhat decoupled from implementation detail. And if I tie that back to the point I was making before about future-proofing yourself, the less you have to be beholden to a particular package or language or environment, the more retargetable you are and the more sellable you are to new things that come along, because you'll be able to adapt and evolve yourself along with the tools that you use. Some other things that patterns do that are really important, they distill experience. So observers didn't just fall out of thin air. They have been documented and implemented and talked about for decades and decades, going back to the early 70s with small talk. This is really where a lot of this stuff first came to fruition in something called the model view controller architecture or architectural pattern, and Observer is a piece of that. Observer was also used heavily in a lot of tool environments for open tool integration, such as ToolTalk, which allowed you to be able to integrate various productivity tools in a networked environment. And Observer was used there to update things. Every time you use Facebook, Observer is being used. You post something to your Facebook page about your status, what's on your mind, and all the people who subscribe to you are notified, and they find out what's on your mind, right? So that's an example of notification. Twitter, same kind of thing. So those are examples of this pattern being used in broader social media environments, not just in user interfaces or networks and so on. Let's talk a little bit more about some common characteristics of patterns. Patterns have some really interesting properties. They are both a thing and a process. This is a really, really profound issue, and it applies to many things in life. So patterns are things in that they describe a particular high-level design or some piece of code and give you the more abstract way of looking at it. So they document something in particular. But they also provide a process that tells you how to make one of those things. And in some sense, that's even more important. So think about mathematics classes you've taken. If you recall, maybe when you were in elementary school or high school, people would try to cram formulas into their head, and they go into the test. And as long as the professor asked them, to sort of do the problems with the formulas that they'd memorized, everything was fine. But the second that you started getting dreaded story problems, right, where you were asked to have to reason about stuff and connect things together, all of a sudden, all the memorization wasn't that helpful unless you got lucky, right? So memorizing formulas those are things, but the process is how to figure out how to do mathematics in a higher order way. Right? So that's more valuable. Being able to reconstitute those things on the fly is often more useful than trying to memorize a lot of stuff. So patterns are both a thing and a process. And there's some nice documents that talk more about this distinction. We're going to talk a lot about these things as we get further into the class, because what you're going to find is there's no possible way you can memorize all the different incantations and realizations of these patterns. They're just endless. Instead, you have to understand the process for applying them, and then you can do them over and over again in lots of different things. It's kind of like going back to the martial arts analogy. If you practice lots of punches and kicks, as long as your assailant comes at you exactly the way that your sensei did when you were learning karate, you'll be fine. But the minute you have to fight 4 hooded ninjas on a bridge with a bow staff, and they're not following the rules anymore, then you're in big trouble, right? Because you don't know the process, you just know the form. Some other nice things about patterns: they can be independent of language and implementation techniques. So a lot of the patterns we're going to talk about, in fact, all the patterns we're going to talk about, can be used in C++ or C or Java or C#, or, God help us, Objective-C, which is the most craziest language, but boy is it popular because you make a lot of money if you know how to program with it, and lots of other things as well. Naturally, not every pattern applies in every way to every language, but you'll see there's a lot of commonality, especially among object-oriented languages. So object-oriented programming languages like Java, C#, C++, to some extent Objective-C, very, very common in the way that they manage patterns and the way they manage state. You start programming in different kind of languages like Scala or FP or Haskell or ML, these functional programming languages. They don't have quite the same patterns that the object-oriented languages do. They don't have the same way of dealing with state. They have lots of patterns, just not quite the same patterns. Another thing that patterns do is they define what's called a microarchitecture, which is really a recurring design structure. So here's the observer pattern. Once again, if you just step back and look at this structurally, you'll see you've got something that kind of contains or manages a bunch of other things, and those other things have some kind of base class that defines certain operations that are virtual, and then you subclass and extend and customize each thing. By the way, the reason for doing this is because oftentimes you want to have different observers behave differently depending on what it is they do best. So a good way to prove this to yourself is take a look at Excel. If you go into Excel and you open up a spreadsheet, you can put formulas into the matrix, and then you can have various observers visualize what's in those cells. And you can visualize the cells as a bar chart, as a histogram, as a pie chart, as a box and whisker diagram. There's all kinds of things you can do with the data in the cells. And you can actually attach them. You can sit there and make changes to the cells, and the observers will automatically update themselves. So the visualizations are all different, but the fact that they're all observers is the same. And so being able to see these similarities and differences in a common way is very important. Certain properties may need to be modified for particular contexts. So here's the basic pattern. Here's an example of the observer pattern in Android. If you take 282 in the fall, you'll learn more about this. So here's an example. There's something that's called a content observable, and you can register various content observers with a content observable. And then when content changes, kind of like the Excel example I just gave you, when content changes, when data is modified, like when a new text message comes in or whatever, you can have something that's a content observable automatically notified on that change to do something or other. And so if you take a look here, you can see that this content observable plays the subject role in the observer pattern. This content observer plays the observer role in the observer pattern. And this my content observer is the concrete observer role in the observer pattern. This is the UML documentation to say what roles these things play in the pattern. Here's a different realization of this pattern, also in Android. So in Android, there's also this concept called a broadcast receiver. Broadcast receivers are basically part of an event-based mechanism for being able to publish and subscribe various events to different applications or different parts of the system when things change. For example, you can register to be notified when battery voltage gets low, or you can register to be notified when the telephone is busy or is available, right? Lots of different things you can register for these different kinds of events. Same thing, same pattern, same pieces, right? Subject, observer, concrete observer, different realization in the form of different classes. So the cool part about this is once you understand this pattern, as you're exposed to the different parts of Android, you feel comfortable, you feel more comfortable because you have some vague idea of what's going on. I was working with one of the TAs, Nolan, on a project that we're doing for this MOOC I'm going to be releasing later this spring. And we came up with a really cool multi-threaded application that plays ping pong, very simple, in multiple threads. And I wrote it using framework and patterns, some of the patterns we're talking about in this class. And then he was able to take it and port it over to Android in no time flat. And he said as he was looking at the code, because it used patterns that we cover here, it was really easy for him to know what to do because it would just basically paint by numbers. Everything just fell into place. Keep in mind that patterns are not code. They're abstractions of design. So you have to reify them, which is just a fancy way of saying implement them in a particular language in a particular context. So here's an example of how you might implement the observer pattern in Java. You would extend the observer class, which is part of the Java libraries. You would have something extend the observable and maybe implement runnable, so that when you went ahead and created an event source, you could go ahead and add the observer to that event source, and then you could go ahead and start a new thread that would generate data and cause the observable to be notified and run, and it would be automatically updating the observer when things happen. You could also implement this thing in C++. Won't talk about that. It's outside the scope of this particular class, but the design is almost identical. The class names are different. The libraries are different, but the design is pretty much the same. Very, very, very powerful forms of systematic reuse. Patterns are not methods. They're not like rational unified method. They're not like Agile or Scrum or things like that. They are an adjunct to methods. They help you be more effective. Patterns are a little bit like accent flavor enhancer. Right? Very few people would sit down and have a meal of accent flavor enhancer. Or it's like salt, right? You wouldn't just eat salt, hopefully. But you would take something that maybe wasn't so tasty and you would sprinkle salt on it, or you'd sprinkle flavor accentuator on it, or you put wasabi sauce and stuff, and then you could actually eat it. I personally can't eat lima beans unless I drown them in mustard, right? Because I don't like the taste. So the point is that patterns are kind of like that. They make other things better. We mostly focus on patterns for code, but there's also patterns about lots of other things that allow people to navigate in very complex environments. There's a lot of good books about patterns for organizing teams in Agile and other styles and methods of writing software. So you may or may not have had enough experience working in teams yet, but when you work in teams, you'll discover there's all kinds of anti-patterns for how not to do things. So there's books on this. There's also a funny book called Dating Design Patterns, which is a pun on the design patterns book, which is the book we're using. And it basically is written for programmers to be more effective on dates. Sometimes a very important skill.